Welcome to The Explainer. Today, we're tackling a concept that quite literally holds our modern world together. It's called the Finite Element Method, or FEM for short. We're going to take those terrifyingly complex differential equations that engineers use to analyze solid structures and fluids, and, well, we're going to break them down into something totally understandable. No sweat, right? Let's get into it.
So to kick things off, we really have to ask a fundamental question. How do engineers actually solve differential equations when they're dealing with real-world, weirdly shaped, complex objects? Classical math is incredibly powerful, absolutely, but it hits a massive brick wall when dealing with non-uniform stuff. The second the geometry of a structure gets unusual or complicated, those classical methods just kind of struggle. They just can't find those exact solutions.
The core of this issue really comes down to the math formulation itself. See, most dynamical equations start out in what's called their strong form. And the strong form is demanding. It demands exact solutions and perfect mathematical smoothness. It's kind of like trying to tailor a single, totally seamless piece of fabric over a really jagged, complex object. It's practically impossible. So to get around this, engineers pivot. They use a weak form or a weighted integral form. This essentially loosens the mathematical rules. It's more like stitching smaller, individual patches together to make a quilt. It naturally incorporates the boundaries of the problem, and that gives us a completely practical pathway to an approximate but highly useful solution. Okay, so here's our roadmap for this explainer. First, we'll unpack the complex engineering problem, then an intro to finite elements, followed by the basic FEM formulas. After that, we'll explore exactly how FEM is used in the real world, and finally, what you'll actually study if you take this on. All right, let's jump right into part one, the complex engineering problem.
Just imagine for a second a one-dimensional metal rod. Both ends are plunged into ice baths. Now, to map the heat conduction across that rod using classical math, you'd have to find one single approximation function that applies to the entire rod, all at once. Now, for a simple straight line, yeah, that's totally manageable. But think about a 3D object with some wild, weird geometry. Trying to find a single mathematical function to cover the whole shebang, it is tremendously difficult. In fact, it's pretty much entirely impossible.
Which brings us to part two, an intro to finite elements. So let's look at the actual definition of the finite element method. Instead of agonizing over finding one impossible mathematical function for a whole complex shape, FEM offers a totally different approach. It's a systematic procedure that takes an extremely complex domain and breaks it down into a collection of geometrically simple subdomains. And those simple subdomains, those are your finite elements. At its core, this is just a brilliant philosophy of divide and conquer. You literally take a massive, totally unsolvable problem, and you just chop it up into tiny, solvable little pieces.
Making this magic happen actually boils down to three main steps. First up, you break the domain down into those simple subdomains, those elements we just talked about. Second, you derive algebraic polynomial approximation functions over each individual element. Because these elements are now so small and so simple, we can safely approximate them using pretty basic math. And then, step three, you assemble all those individual elements right back together based on the continuity of the overall solution. So to recap, chop it up, approximate the math for each tiny piece, and then glue it all back together. Beautiful, right?
Moving right along to part three, the basic FEM formulas. Now, I know what you might be thinking. The math must be horrible. But when you actually strip away all the terrifying high-level calculus, it is such a relief to find that what's left is this really elegant system of matrix algebra. Right at the core of it, you have the fundamental equation for static linear analysis. It's just k times u equals r. By breaking the domain down into those finite elements, all those nasty complex differential equations just transform into these nicely compacted element matrices. And guess what? Computers can solve those incredibly fast.
Let's actually map these variables to physical realities so it makes sense. That K-matrix, that represents the overall system stiffness. The U vector represents nodal displacement, basically how much the points actually move. And R is the applied force. So quite simply, stiffness times displacement equals force. Now, when you want to introduce movement and vibration over time, it's pretty straightforward. You just add an M matrix for system mass and a C matrix for damping. You feed that to the computer, it evaluates the matrices, crunches the numbers, and spits out the element stresses.
Okay, part four, how FEM is used. We know the math, but the history here is wild and really shows the explosion of this method. Get this, the foundation was actually laid way back in 1870. Lord Rayleigh was using these early variational methods to figure out acoustic vibrations in pipe organs. Fast forward to the 1950s, and Boeing Aircraft formally launches a project using these concepts to figure out the stresses in airplane wings. But here's the catch. Because FEM relies on those massive matrices we just talked about, it didn't truly take off until the late 70s and 80s when computers finally became affordable enough to handle the math. Today, there are well over 25,000 published papers on FEM, and it's a completely ubiquitous tool across almost every engineering industry you can think of.
So yeah, today, industries rely heavily on FEM for solid, structural, fluid, and heat transfer analysis. But I'll tell you where it truly shines. It's in what engineers call coupled problems. Think about a railway wheel for a second. As the train moves, the wheel experiences friction, right? And that friction generates immense heat. Using FEM, engineers can run a coupled analysis to see exactly how that rising temperature creates structural stress, and vice versa, all at the same time. They can zoom in and analyze incredibly complex stuff, like the contact plastic strains happening at the exact microscopic point where the steel wheel touches the rail. It is precisely because of these incredibly detailed coupled analyses that our modern high-speed trains, planes, and cars are